Good evening and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. We are going to be looking at some more Calc 2 subjects. Again, this is kind of my first draft of what I'm going to be doing during class this semester, and get into anything that people request if anybody stops on by. So, feel free, if you're one of those people who has questions, stop on by now or in a future stream. I will always be doing Wednesday nights unless something important comes up. Or if I decide to take a vacation, whatever. So Wednesday nights are going to be my nights I'm pretty much always going to be here. Monday mornings I've been trying to get off the ground, but lately it's just not working. So maybe, maybe not. We'll see how it goes. And again, gaming streams on Friday nights. Lately we have been getting back into Control because Control is a pretty awesome game. I did lose access to my Xbox, unfortunately, so, or rather, it's very slow. So I've been catching the PC version back up to where I was, and I'm pretty close. In terms of calculus, we had been talking about, okay, now you know what, this is not, alright, whatever. This is not quite where we were before, but whatever. Window's been resized a bit. Alright, so for tonight we're going to be talking about improper integrals. That's pretty ugly. Yeah. Oh, you know what? That's why. We're just really far zoomed out. That just looks weird. Alright, let's try this again. Alright, so integrals are called improper if we're starting to look at questionable things that are going on with all of our integration. So, for instance, one example of that might be, why is that changing color? That's slightly alarming. Well, it's still coming through, and it's still coming through here, so okay. We'll just go with it. So one of the things that, for instance, we've been told you can't do that is anytime that you have an integral that involves some sort of infinite object, whatever it might be. So for instance, if we were to have a function y equals 1 over x, and if we wanted to integrate this 1 over x dx from, for instance, 0 to 1, or from, let's say, 1 to infinity, or any sort of other stuff that could be going on here, we're going to end up with problems due to the fact that when we take the integral of these things, we end up with logarithms, and then when we're trying to do log of 0, that creates a bit of an issue, and also log of infinity. What exactly are we supposed to do with these things? So, improper integrals offers us a solution for this, basically whereby you just take whatever you didn't like about this stuff, and you could just replace it with a variable, at least temporarily. So we take integral from a to b of f of x dx, where f has a discontinuity at some c inside of a to b. Could be the endpoints, that's okay, like we did here. That's perfectly fine. Or if a or b are infinite. All right, in either of these cases, we're also going to end up with same stuff. So there is an issue here if we end up with infinite values, or some number c within a to b is discontinuous. So what we can do with this is we say, okay, we'll take the integral of f of x dx, and we get capital F of x, normally plus c, but again, here we're using a definite integral, so we can kind of ignore that. Okay, so when the integral of f of x dx is capital F of x plus c, then we end up with the integral from a to c of f of x dx plus the integral from c to b f of x dx Then here we're going to end up with capital F of c minus capital F at a, plus over here capital F at b minus capital F at c. And then with these, we have to take into account the fact that, again, we don't know exactly what capital F at c is. It's discontinuous from above, so what we're going to have to do is say that this is going to be the limit as x approaches c, capital F of x minus f at a plus f at b minus limit x approaches c of capital F of x. Now keep in mind, right, these limits might not be the same exact thing. So if we have a discontinuous object that looks like this, then we're going to have two separate limits, and that could create some interesting differences within all of this. So maybe these are one-sided limits, really, is what we're going to be looking at. So this is C and A, so we're coming from the negative side here, and we're coming from the positive side on this one. And with those being, again, separate limits, they could potentially have different values. music appears to have crashed. Hang on one sec. Yep, I appear to have broken pretzel rocks. So, we may not have any more music for the time being. But that's alright. Oh, cool. I updated my headphone software and it needs to be restarted, or the whole computer needs to be restarted before I can use that again. So there's a possibility that Pretzel Rocks is somehow tied to that. Huh. Oh well. Or I could just restart it and it works fine. Alright, cool. When in doubt. Alright, so in the case of A or B being infinite values, we're basically going to do the same thing. We're going to take the limit as x goes to some value c, or we could just call it a or b depending on what it is, instead of actually writing an infinity symbol, because technically you're not supposed to write an infinity symbol in the middle of a calculation. That is, as it says above, improper. So, improper. So in the case of something like this example here, we could have that the integral as we go from 1 to infinity of 1 over x dx is then equal to the natural log of x as we go from 1 to, we'll just call it b, and then have to take the limit as b approaches infinity. So when we look at this, this is saying that we're going to do the limit as b approaches infinity of the natural log of b minus the natural log of 1. Natural log of 1 is 0. And so we are just left with this limit. Now the thing is that as as b goes off to infinity, the natural log also continues to rise forever. It will never reach a particular value. So because of that, this whole thing is going to have an infinite value itself. So the integral will end up being an infinite value. We have an infinite area underneath that particular curve. Alright, some more interesting examples might be something like integral of, as we go from 1 to infinity, of 1 over x squared dx. Which, as we look at this, This is going to be a, well, it's a -2, so we need a negative to be brought out, or we can use that as part of our power rule, right? So we have a -2. We want to increase the value of our exponent. It's going to become -1, so that's 1 over x. And again, plus c, but it's a definite integral, so we can ignore that. And then we go from 1 to b, the endpoint again. And again, we have to move all this over here. Take the limit as b approaches infinity of -1 over x. This is going to be equal to a limit as b goes to infinity of -1 over b minus a -1 over 1, which is the limit as b approaches infinity of -1 over b plus 1. And what we have here is that b is going to approach infinity. That's -1 over something very large. This whole thing here will just become 0. And then plus 1. So the area for 1 over x squared dx, or the area under the curve 1 over x squared, from 1 to infinity is just going to be 1. We could do this with all sorts of individual problems. All right, you don't have to necessarily use a constant, but it needs to be constant with relation to the variable that's in use. So for instance, if you're using your limit of integration here as we're going off to infinity, you could call it t instead of b. Just call it like a different variable, that's fine too. All right. This is one of the integrals that I absolutely hate, so let's do it. Seems interesting when I say that, I'm sure. When we look at something like the integral from 1 to infinity of 1 over x natural log x dx, this always ends up being something very interesting. You look at it and you can't actually do anything with the integral just by itself as it sits right now. However, one of the things you can do is do a u substitution. So if we think about this and say, all right, which function do we have just a function of, and then what is its derivative? So there are kind of two functions here. We have the overall functions 1 over x and 1 over natural log of x. And if we just look at them in whatever place they're in, we have what looks like x and a natural log of x. These are our two separate functions. So these in-place functions are going to become our u's, and the overalls can become du's. So if we look at the combination of any one of these, no, it doesn't necessarily always have to be like this. It could be that one of our overalls could be a u, and one of the in places could be a du. It's not very likely though. So this is just kind of like how I'm typically looking at it. If you notice this combination here, what we've got is one of the overall here can be 1 over x times dx, and a function that's just kind of randomly stuck in there is natural log of x. 1 over natural log of x, if we look at this, there's not really a whole lot we can do with it. You know, whether it's in yep, whether it is 1 over natural log of x, or if it is like the du that we're supposed to get, like I don't know any particular integrals that are going to yield this, nor do I know the integral of this thing. So that's really not helpful. Therefore, if we look at the other one, right, 1 over x, I know that the integral of 1 over x is going to be a natural log. I know that the derivative of 1 over x is going to be negative 1 over x squared. Do I have either of those things? Right, I have a natural log. It's just that it's in the bottom. So what do we do to deal with this? Well, we let, in this particular case, u be equal to the natural log of x. We let du, that's off the page. Might as well. Let du equal 1 over x dx. And now I've got a pair, right? This actually is here in this function. So 1 over x dx is going to become du. Natural log of x is just going to become u. It's in the bottom. So this is now 1 over u du. We're taking the integral as x goes from 1 to infinity. This is a really important distinction that you make, by the way, that x has these limits and u does not. So the other option is that you change the limits and you say, okay, what are the limits of integration going to be if we let 1 go into these places? So if 1 is put into natural log of x, we get a 0 back. So you could, in fact, write this as u equals 0, 1 over u du. And then we get an infinite value into a natural log of x, which is going to be an infinite value. So u is going to go from 0 to infinity, whereas x is going to go from 1 to infinity. If you do choose x as your limits of integration that are going to stay there the whole time, you need to remember to convert back. If you are going to use u, you don't actually have to convert back. You can just leave it as the integral that you're going to find here. So u equals 0 to infinity of, we already know what this integral is, right? Du over u, or 1 over u du, is going to end up being the natural log of u and u is going to go from 0 to infinity. We get a bit of a problem here in that you can't plug in u into a natural log. Alright, sorry, you can't plug 0 into a natural log. And then up here we're going to get an infinite value, so that's not really helpful either. Take the limit as u goes to infinity. No, sorry, not u. Again, you can use t or you can use something else, not x, not u. So I guess b goes to infinity. We'll just use a and b as the limits of integration because that makes it easier. Of the natural log of b minus limit as a goes to 0 of natural log of a. This also creates a bit of an issue. Actually, no, it doesn't. We good? Alright, if we were to evaluate this, b is going to infinity, the natural log of b is going to be infinity. This is then going to be a minus natural log of a, when a is going to 0, is going to get us a negative infinity here. So this is going to get us infinity plus infinity, which is going to just be an infinite value. Yep. Alright, so this is how that works. We could, again, instead of using u, we could have used this with x instead. You do the same integration, you still end up with the natural log of u, where, but this time we say that x is going from 1 to infinity, and then here you say, well, if x is 1, here we have to trade this back out. This is the natural log of x. Evaluated, x goes from 1 to infinity. Either way, this ends up being the same stuff. Due to the fact that the final limit of integration is going off to infinity, right? So our b is going off to infinity, and our a value is going to 1 inside this double natural log. So the natural log of 1. Natural log of 1 is 0, and now we've got the natural log of 0, which is undefined, negative, approaching negative infinity. So then you have to plug in the proper values to make sure that that all works. Right. So one of the other